Hello there, and welcome to Space Historians. I'm so glad you found your way here tonight. Take a moment to settle in, to let the day begin its slow fade behind you. Let your shoulders drop just a little. Where in the world are you watching from tonight? A quiet bedroom where the stars might be visible through your window? A cozy corner where the universe feels both impossibly far and somehow close? Wherever you are, you're welcome here. Tonight we're going to explore one of the most remarkable discoveries in the history of astronomy. 300 galaxies that, according to everything we thought we knew about the universe, simply should not exist. The James Webb Space Telescope found them anyway, shining impossibly bright in the deep darkness of the early cosmos. We'll discover what makes these galaxies so confounding, understand how they challenge our most fundamental theories about how the universe grew from simplicity to complexity, and contemplate what it means when the universe refuses to follow the rules we've written for it. It's a journey that spans 13 billion years, from the first moments after the Big Bang to the present day, from the smallest particles to the largest structures in existence. But don't worry, this isn't going to be a frantic race through incomprehensible physics or an alarmist proclamation that everything we know is wrong. Instead, we'll move slowly and carefully through this cosmic mystery, taking our time with each discovery, each piece of evidence, each beautiful complication. By the end, I think you'll find not confusion but wonder, not anxiety but a deep appreciation for how much remains to be understood about the universe we call home. If you enjoy these calm explorations of cosmic mysteries, a like and subscribe really helps reach others seeking the same peaceful way to end their day. And to those already subscribed, thank you for being here, for trusting me with these quiet hours. So settle in now, let your breathing slow, take a deep breath, and release whatever tension you're carrying from the day. Let's begin our slow drift through the impossible galaxies, through the deepest mysteries of cosmic time. There's nowhere you need to be right now, nothing you need to solve or understand urgently. Just listen, and let the story of the universe unfold. Let yourself rest. The light took 13 billion years to reach us. 13 billion years of travelling through expanding space, of crossing distances so vast that human minds struggle to hold them. And when that ancient light finally arrived, in the summer of 2022, it told a story that no one expected to hear. The James Webb Space Telescope had been operational for less than 6 months. Its enormous gold-plated mirror, nearly 21 feet across, was still being calibrated, still learning to see with unprecedented clarity into the deepest reaches of cosmic time. The telescope hangs in space, roughly 1 million miles from Earth, at a gravitational balance point called L2, where it can stare uninterrupted into the darkness. Its instruments cooled to near absolute zero to detect the faintest whispers of infrared light from the universe's distant past. In those early months of operation, astronomers pointed Webb at a region of space that appeared empty to most telescopes, just darkness between the brighter nearby stars. But Webb, with its extraordinary sensitivity to infrared light, could see what others could not. It could peer through cosmic time itself, back to an era when the universe was young, when everything was closer together, when the first structures were just beginning to form from the primordial darkness. What Webb saw changed everything. The images came back showing not the expected scattering of faint, small, primitive galaxies, but instead revealed hundreds of galaxies that were bright, massive, and fully formed. Galaxies that looked, in many ways, like the mature spiral and elliptical galaxies we see in our local universe today, except these were shining at us from a time when the universe was only a few 100 million years old. To understand why this discovery sent shockwaves through the astronomical community, you need to understand what we thought we knew about how galaxies form. The Standard Model, built over decades of observations and confirmed by countless pieces of evidence, told a clear story. The early universe should have been simple. After the Big Bang, matter was distributed almost perfectly evenly throughout space, with only the tiniest fluctuations in density. Over hundreds of millions of years, gravity would slowly, patiently amplify these tiny fluctuations, pulling matter together into larger and larger clumps. First came small dwarf galaxies, then these merged to form larger galaxies, then those merged to form even larger ones. It was a bottom-up process, a gradual assembly line from simple to complex, from small to large. The problem is that this process takes time, enormous amounts of time. Current models suggest it should take at least 500 million years, perhaps closer to 1 billion years, for gravity to gather enough matter to build the massive galaxies we see in our local universe. And yet here was Webb showing us galaxies that appeared to have accomplished this feat in a fraction of that time, when the universe was impossibly young. This discovery raises a gentle question that astronomers are still grappling with. How did the universe build such massive organised structures so quickly? How did gravity work fast enough to assemble billions of stars into coherent galaxies when there simply shouldn't have been enough time? The answer, as we'll explore throughout this journey, may require us to rethink some of our most fundamental assumptions about how the cosmos evolved from the simplicity of the Big Bang to the rich complexity we observe today. Before we can fully appreciate the impossibility of what Webb discovered, we need to travel back to the beginning, to a time when the universe contained no galaxies at all, no stars, no light. A time astronomers call the cosmic dark ages, and it's precisely as mysterious as it sounds. The story begins, as all cosmic stories must, with the Big Bang. 13.8 billion years ago, the universe emerged from a state of unimaginable density and temperature. In those first fractions of a second, space itself expanded faster than light can travel, a period called cosmic inflation that set the initial conditions for everything that would follow. The universe cooled as it expanded, and within minutes, the first atomic nuclei formed, mostly hydrogen with a smaller amount of helium. But the universe was not yet transparent. It was filled with a hot, dense plasma, a soup of electrons and nuclei that scattered light in every direction, making it impossible for photons to travel any significant distance. The cosmos was bright but opaque, like being inside a glowing fog. This changed roughly 380,000 years after the Big Bang. When the universe cooled enough for electrons and nuclei to combine into the first complete atoms. This moment, called recombination, is when the fog cleared, when the universe became transparent to light for the first time. The photons that were freed at this moment are still travelling through space today. We detect them as the cosmic microwave background radiation, that faint glow of ancient light that fills the entire sky, carrying within it the subtle imprints of the density fluctuations that would eventually become galaxies and clusters of galaxies. After recombination came darkness. With the hot plasma gone and no stars yet formed, the universe entered the cosmic dark ages. Imagine it if you can, a vast expanding space filled with hydrogen and helium gas, completely dark except for the gradually red-shifting glow of the cosmic microwave background. No stars to light the darkness, no galaxies to break the monotony, just endless clouds of neutral gas, slowly, imperceptibly, beginning to clump under the patient pull of gravity. This dark period lasted for tens of millions of years, perhaps as long as 100 million years, though the exact duration remains uncertain. During this time, the tiny density fluctuations imprinted during inflation were growing. Regions that were slightly denser than average had slightly stronger gravity, which attracted more matter, which increased their gravity further, in a self-reinforcing cycle that gradually, achingly slowly, pulled the smooth distribution of gas into denser and denser knots. The Dark Ages ended with what astronomers call the cosmic dawn, the moment when the first stars ignited. These were not stars like our Sun. They were massive, perhaps 100 or even 200 times the mass of our Sun, formed from pristine hydrogen and helium that had never been processed through previous generations of stars. They burned incredibly hot and bright, and they lived fast, consuming their fuel in just a few million years before exploding as supernovae. Seeding the universe with the first heavier elements, the light from these first stars began to transform the universe through a process called ionization. The energetic ultraviolet photons from early stars had enough energy to strip electrons from hydrogen atoms, turning the neutral gas that filled space back into plasma, but this time a much thinner, more diffuse plasma than existed before recombination. This ionization gradually spread through the universe, taking hundreds of millions of years to complete, creating expanding bubbles of ionized gas around the first galaxies. What we thought we understood was the timeline of this process. The first stars should have formed around 100 to 200 million years after the Big Bang. The first small galaxies should have assembled by 200 to 300 million years. These dwarf galaxies would then gradually merge over the next billion years to form the large galaxies we see today. But the galaxies Webb discovered don't fit this. Timeline. They appear fully formed at times when our models say only small dwarf galaxies should exist, raising profound questions about whether our understanding of the Dark Ages and cosmic dawn is fundamentally incomplete. The first hints that something unexpected was happening in the early universe came from Webb's very first deep field images, released to the public in July of 2022. The images were breathtaking, showing thousands of galaxies scattered across a tiny patch of sky, each one a separate island universe containing billions of stars. But it wasn't just the beauty that caught astronomers' attention, it was the distribution. Among the thousands of galaxies in those early images were dozens that appeared to be at extremely high redshift, meaning they were incredibly far away and incredibly old, their light coming from the universe's earliest epochs. Redshift is the key to understanding cosmic distance and time. As the universe expands, the space between galaxies stretches, and this stretching affects the light travelling through that space. Photons emitted as short wavelength blue light get stretched into longer wavelength red light, with the amount of stretching directly related to how much the universe has expanded since the light was emitted. Astronomers measure this stretching as a number called redshift, denoted by the letter Z. A galaxy at redshift 0 is right next to us. A galaxy at redshift 1 is about halfway across the observable universe, and galaxies at redshift 10 or higher are showing us light from when the universe was less than 500 million years old. In those first Webb images, astronomers identified galaxies with provisional redshifts of 10, 11, even 13 or higher. These were candidates requiring spectroscopic confirmation to verify their distances, but the sheer number of high redshift candidates was immediately surprising. Early predictions suggested Webb might find a handful of such distant galaxies in its deep surveys. Instead, it was finding dozens, then hundreds. As more observations accumulated throughout late 2022 and into 2023, the picture became clearer and more puzzling. Many of these high redshift candidates were confirmed through detailed spectroscopy, which splits the light from each galaxy into its component wavelengths, revealing characteristic patterns that definitively measure the redshift. And these confirmed galaxies were not behaving as expected. They were too bright. According to standard models, galaxies in the very early universe should be faint and difficult to detect, even for a telescope as powerful as Webb. They should be small, containing perhaps a few tens of millions of stars, still in the early stages of assembly. But many of the galaxies Webb was finding appeared to contain billions of stars, masses comparable to the Milky Way, all packed into a universe that was only 300 to 500 million years old. One galaxy in particular, catalogued as JWST 13-0, captured attention. Spectroscopy confirmed its redshift at 13.2, corresponding to light emitted just 330 million years after the Big Bang. This galaxy appeared to contain several billion stars and was actively forming new ones at a rate of dozens per year. It wasn't a small proto-galaxy gradually assembling itself. It was already massive, already mature, already behaving like galaxies billions of years older. The discoveries kept coming. Another galaxy, found at redshift 11.5, showed evidence of a supermassive black hole at its centre, with a mass millions of times that of our Sun. This was deeply problematic because black holes grow by accreting matter over time. And supermassive black holes were thought to require hundreds of millions of years or more to reach such enormous sizes. Yet here was one that had somehow grown to maturity when the universe was barely 400 million years old. By early 2023, astronomers had compiled a list of hundreds of these impossibly early, impossibly massive galaxies. The list included galaxies with stellar masses exceeding 10 billion solar masses, galaxies with complex structures showing bars and spiral arms that shouldn't have had time to form, and galaxies with colours indicating they contained old stellar populations that somehow already existed in the cosmic dawn. The astronomical community found itself facing a profound puzzle, one that couldn't be easily dismissed or explained away by observational error. The galaxies were real. Their redshifts were confirmed, their properties were measured, and they fundamentally contradicted the standard model of galaxy formation that had been refined over decades of careful observation and theoretical work. This tension between observation and theory is where science becomes most interesting, most alive. And it's this tension that we'll explore as we continue our journey through the impossible galaxies. To understand why Webb's discoveries are so revolutionary, we need to explore the beautiful, intricate theory of galaxy formation that astronomers spent decades constructing. This theory, often called the lambda CDM model, has been remarkably successful at explaining the large-scale structure of the universe, making it all the more shocking when observations challenge its predictions. The lambda CDM model rests on several foundational pillars. Lambda refers to dark energy, the mysterious force causing the universe's expansion to accelerate. CDM stands for cold dark matter, a hypothetical form of matter that doesn't interact with light but exerts gravitational influence. Together with ordinary matter, and dark energy, this model describes how the universe evolved from the nearly uniform conditions after the Big Bang to the rich tapestry of structure we observe today. In this framework, dark matter plays the starring role in galaxy formation. Dark matter makes up approximately 85% of all matter in the universe, meaning it utterly dominates the gravitational landscape. After the Big Bang, dark matter began clumping together under its own gravity, forming what astronomers call dark matter halos, invisible scaffolding upon which galaxies would eventually form. The process begins with tiny fluctuations in density, variations of less than 1 part in 100,000 in the early universe. These fluctuations, imprinted during cosmic inflation and visible today in the cosmic microwave background, provided the seeds for all structure formation. Regions that were slightly denser than average had slightly stronger gravity, allowing them to attract nearby matter, growing slowly denser over time. This growth follows predictable mathematical rules derived from gravitational physics. Small dark matter halos form first, gathering together perhaps 1 million or 10 million times the mass of the Sun. Over hundreds of millions of years, these small halos merge to form larger ones, which merge to form even larger ones, in a hierarchical process that builds complexity from the bottom up. Ordinary matter, mostly hydrogen and helium gas, falls into these dark matter halos, settling into rotating disks or irregular clouds depending on the halo's properties and history. As the gas becomes denser, it begins to cool by radiating away energy. Eventually, in the densest regions, the gas becomes dense and cold enough for gravity to overcome the gas pressure, causing the cloud to fragment into clumps that collapse further, heating as they contract until nuclear fusion ignites and stars are born. This process takes time. Current simulations suggest that the first small galaxies, containing perhaps 10 million to 100 million stars, should form around 200 to 300 million years after the Big Bang. These early galaxies were thought to be irregular, lacking the organized structures like spiral arms or central bulges that we see in mature galaxies today. Over the next billion years, these small galaxies gradually merge, driven by gravitational interactions and the ongoing accretion of gas from the intergalactic medium. Each merger adds mass, triggers bursts of new star formation, and slowly builds the larger, more massive galaxies that dominate the universe today. The Milky Way itself is thought to have formed through this process, accumulating dozens of smaller galaxies over billions of years. With evidence of ancient mergers still visible in stellar streams and satellite dwarf galaxies that orbit our own, this hierarchical merging model made clear predictions about what deep observation should reveal. Looking back to when the universe was young, telescopes should find mostly small, irregular, faint galaxies. Massive galaxies like the Milky Way or Andromeda should be rare or absent in the early universe. Large galaxies should become progressively more common as we look at more recent cosmic epochs, as mergers accumulate mass over time. Previous deep surveys conducted with the Hubble Space Telescope largely confirmed these predictions. Hubble's observations reached back to when the universe was about 500 million to 1 billion years old. And the galaxies it found at those distances were generally small, irregular, and less massive than nearby galaxies, exactly as the hierarchical model predicted. But Webb, with its superior infrared sensitivity and larger mirror, could see further back and detect fainter galaxies than Hubble ever could. and what it revealed was a population of galaxies that don't fit the hierarchical framework, galaxies that appear to have assembled their mass far too quickly, challenging the careful theoretical edifice that astronomers had constructed over decades of dedicated work. By the end of 2023, the number had crystallized. 300 galaxies, perhaps slightly more depending on exact selection criteria, that seemed to violate the fundamental expectations of galaxy formation theory. 300 separate challenges to what we thought we understood about how the universe builds complexity from simplicity. These galaxies weren't clustered at a single cosmic epoch. They were spread across a range of times, from about 300 million years after the Big Bang to around 800 million years, covering the cosmic dawn and the early portion of what astronomers call the epoch of Rayonization. Some were more extreme than others, but all shared the characteristic of being more massive, more luminous, or more structurally mature than theoretical models predicted they should be at their respective ages. The statistics were striking. If you simply counted the number of massive galaxies that Webb found at high redshift, and compared that to the predictions from standard galaxy formation simulations, there was a mismatch of roughly a factor of 10. The universe had produced 10 times more massive galaxies in the early cosmic epochs than it should have been able to produce given the available time and the known efficiency of star formation. Several galaxies became particularly famous in the astronomical literature, serving as prime examples of the crisis. Galaxy C EERS-93316, initially thought to be at redshift 16 but later revised to a still impressive redshift of around 4 to 5, showed us how even the redshift estimates were pushing the boundaries of what instruments could reliably measure. The most distant confirmed galaxies consistently appeared at redshifts between 11 and 13, corresponding to the universe at ages between 300 and 500 million years old. What made these galaxies impossible wasn't just their masses, though that alone was problematic. It was the combination of properties they displayed. Many showed evidence of significant dust, which forms from heavier elements produced in stars and distributed by supernova, implying that multiple generations of stars had already lived and died. This requires time, more time than was available in the young universe these galaxies inhabited. Others showed complex morphologies, featuring distinct structures like bars, bulges, and disk components that form through gravitational interactions and dynamical processes that, again, were thought to require hundreds of millions of years to develop. Yet here they were, fully formed when the universe was barely out of its infancy. The star formation rates added another layer of mystery. Many of these early galaxies appeared to be forming stars at rates of tens or even hundreds of solar masses per year, rates comparable to or exceeding the most vigorous star-forming galaxies in the more recent universe. Where was all this gas coming from? How was it being funneled into these galaxies fast enough to sustain such prodigious star formation? The standard model assumed that gas accretion would be relatively slow in the early universe, limited by the rate at which gas could cool and fall into dark matter halos. Some of the galaxies displayed evidence of supermassive black holes, objects containing millions to billions of solar masses concentrated in regions smaller than our solar system. The growth of supermassive black holes is limited by a fundamental physics constraint called the Eddington limit, which sets a maximum rate at which a black hole can accrete matter without the radiation pressure from the infalling material blowing away the surrounding gas. Even if black holes started growing from the very first stars and accreted at the Eddington limit continuously, current models struggle to grow them to the observed masses in the available time. Faced with this overwhelming evidence, the astronomical community had to confront several possibilities. Perhaps the observations were wrong, though as more data accumulated and measurements were refined, this explanation became increasingly untenable. Perhaps our theoretical models were missing something fundamental about how quickly galaxies can assemble in the early universe. Or perhaps our understanding of cosmology itself, the lambda CDM framework that describes the universe's evolution, needed revision. What's remarkable about this moment in astronomy is the humility it requires. Scientists spent decades building and refining these models, confirming them with observation after observation, publishing thousands of papers, and now the universe, through the eye of the James Webb Space Telescope, seems to be suggesting that something in this carefully constructed edifice is incomplete, that despite all our progress, we're still missing crucial pieces of the cosmic puzzle. And that realization, far from being discouraging, is precisely what makes this discovery so thrilling, so worthy of our contemplation as we drift deeper into this story together. One of the most profound implications of the impossible galaxies centers on dark matter, that invisible substance that makes up most of the matter in the universe and plays the dominant role in structure formation. The crisis Webb has created forces us to reconsider what we think we know about how dark matter behaves and whether our understanding of it is complete. Dark matter was first proposed in the 1930s by astronomer Fritz Zwicky, who observed that galaxies in the Coma cluster were moving far too fast to be held together by the gravity of visible matter alone. Something invisible, something that didn't emit or absorb light, had to be providing additional gravity. For decades, this remained a curious anomaly, but by the 1970s and 80s, observations of galaxy rotation curves provided overwhelming evidence that individual galaxies were embedded in massive halos of dark matter, extending far beyond the visible stars. We still don't know what dark matter actually is. The leading hypothesis proposes that it consists of weakly interacting massive particles, or WIMPs, that were created in the early universe and interact only through gravity, and possibly the weak nuclear force. Despite decades of experiments trying to directly detect dark matter particles, none have succeeded, leaving dark matter's fundamental nature mysterious, even as its gravitational effects are measured with increasing precision. What we do know about dark matter comes from how it affects the visible universe. Computer simulations that follow the evolution of dark matter from the early universe to the present day have been remarkably successful at reproducing the large-scale structure we observe. The cosmic web of filaments and voids, the distribution of galaxy clusters, the patterns we see in the cosmic microwave background. These successes gave astronomers confidence that they understood dark matter's role in cosmic evolution. But these same simulations make specific predictions about galaxy formation timescales, predictions that Webb's discoveries now challenge. In the standard picture, dark matter halos grow through a hierarchical process, with small halos forming first and gradually merging to form larger ones. The rate at which this happens is governed by the properties of dark matter and the expansion of the universe. The problem is that this process appears to be too slow to produce the massive galaxies Webb has found. If dark matter is cold, meaning the particles move slowly compared to the speed of light, then structure formation proceeds at a certain pace dictated by how quickly gravity can amplify the initial density fluctuations. Simulations using cold dark matter consistently predict that massive galaxies should be rare in the early universe, appearing commonly only after the universe is at least 1 billion years old. This has led some physicists to wonder whether dark matter might not be entirely cold. Perhaps it includes a component of warm dark matter, particles that move faster and have more kinetic energy, or perhaps there are interactions between dark matter particles that we haven't accounted for that could speed up the collapse and merger processes. Some have even proposed more exotic scenarios involving dark matter that interacts with itself through forces other than gravity, creating what's called self-interacting dark matter. Another possibility focuses on the initial conditions, the fluctuations imprinted during cosmic inflation. Standard inflation models predict that these fluctuations should have a specific statistical character, with most of the power in large-scale variations and less in small-scale ones. But perhaps inflation produced more small-scale fluctuations than expected, giving dark matter more concentrated seeds from which to grow, allowing earlier and faster galaxy formation. These alternative ideas aren't without problems of their own. Warm dark matter, for instance, helps produce earlier galaxies but struggles to explain other observations, like the abundance of dwarf galaxies orbiting larger ones. Self-interacting dark matter has similar issues, solving some problems while creating others. And modified inflation models need to remain consistent with the precise measurements of the cosmic microwave background, which severely constrains how much the initial conditions can deviate from standard predictions. What makes this particularly fascinating is that dark matter has become so central to our cosmological framework that questioning it feels almost revolutionary. For decades, astronomers have gathered evidence supporting the existence and properties of dark matter, from gravitational lensing observations that map its distribution to cosmic microwave background measurements that constrain its abundance. Yet the impossible galaxies suggest that perhaps some aspect of this picture remains incomplete, that our confidence in the standard dark matter model might be premature. There's a certain beautiful irony here that we don't yet fully understand the substance that makes up most of the matter in the universe, and now observations suggest our incomplete understanding might be even more incomplete than we thought. Among the impossible galaxies Webb has revealed, some of the most perplexing contain supermassive black holes that shouldn't exist yet, objects millions to billions of times the mass of our Sun that appear to have formed and grown to maturity in what seems like impossibly short time. Black holes form when massive stars exhaust their nuclear fuel and collapse under their own gravity, creating regions where gravity is so strong that not even light can escape. These stellar mass black holes typically contain between 5 and 100 times the mass of the Sun. But the black holes at the centres of galaxies are far more massive, containing millions or even billions of solar masses, and how they grow to such enormous sizes remains one of astrophysics' most intriguing questions. The challenge is time. A black hole grows by accreting matter, pulling in gas, dust, and occasionally entire stars from its surroundings. But this accretion process is limited by a fundamental constraint discovered by Arthur Eddington in the 1920s. As matter falls toward a black hole, it heats up and radiates energy, mostly in the form of X-rays and ultraviolet light. If the black hole tries to accrete too quickly, this radiation becomes so intense that it creates outward pressure on the surrounding gas, counteracting gravity and preventing further infall. This Eddington limit sets a maximum growth rate. A black hole accreting at the Eddington limit continuously would double its mass roughly every 50 million years. Starting from a stellar mass black hole of, say, 100 solar masses and accreting at the Eddington limit for 500 million years, you could theoretically grow a black hole to about 100,000 solar masses, nowhere near the millions to billions of solar masses observed in supermassive black holes. For decades, astronomers assumed that supermassive black holes grew gradually over cosmic history, starting from stellar mass seeds in the early universe and spending billions of years accreting matter and merging with other black holes during galaxy mergers. This gradual growth scenario worked well for explaining the supermassive black holes we observe in the relatively nearby universe, but it makes specific predictions about what we should find when we look back to the cosmic dawn. Webb has found supermassive black holes that violate these predictions. Several galaxies observed at redshifts between 9 and 11, corresponding to when the universe was between 400 and 600 million years old, show spectroscopic signatures indicating the presence of black holes with masses exceeding 1 million solar masses. Some appear even more massive, approaching 10 million to 100 million solar masses. These observations create what astronomers call the supermassive black hole seed problem. How do you get from stellar mass black holes to supermassive ones in the available time? Even if the black holes started forming with the very first stars at around 100 to 200 million years after the Big Bang, and even if they accreted at the Eddington limit continuously without interruption, the math doesn't work. They can't grow massive enough fast enough. This has led researchers to propose several creative solutions. One possibility is that the first black holes didn't form from stars at all, but instead formed directly from the collapse of massive gas clouds in the early universe, creating what are called direct collapse black holes. These could have initial masses of thousands or even hundreds of thousands of solar masses, giving them a head start in the race to become supermassive. But creating direct collapse black holes requires very specific conditions: gas clouds that remain pristine, never contaminated by heavy elements from earlier stars, and environments where the gas can't fragment into smaller clouds that would form stars instead of black holes. Another possibility is that early black holes somehow violated the Eddington limit, accreting matter faster than standard physics would predict. This super-Eddington accretion might occur in particularly dense environments where gas is funneled toward the black hole faster than radiation pressure can expel it, or it might involve configurations where the accreting material shields itself from the radiation, allowing matter to fall in from multiple directions simultaneously. Some theorists have proposed that mergers between black holes could accelerate the growth process. If galaxies in the early universe merged frequently, their central black holes would eventually coalesce, combining their masses. but galaxy mergers are relatively rare events, and merger-driven growth still struggles to produce supermassive black holes quickly enough to explain Webb's observations. The presence of these early supermassive black holes also has implications for galaxy evolution itself. When black holes accrete matter, they release enormous amounts of energy in a process called active galactic nucleus feedback. This energy can heat and expel gas from the galaxy, regulating star formation and affecting the galaxy's growth. The fact that supermassive black holes were already present and active in the cosmic dawn suggests this feedback process was influencing galaxy evolution far earlier than previously thought, adding yet another layer of complexity to the puzzle of how galaxies assembled their mass so quickly. What's humbling about this problem is how it exposes the limits of our understanding across multiple domains of physics, from stellar evolution to accretion physics to gravitational dynamics, all connected through the thread of cosmic history. One of the more subtle but equally troubling discoveries from Webb's observations of early galaxies involves dust, those tiny particles of carbon, silicon, iron, and other heavy elements that seem mundane but whose presence in the cosmic dawn creates profound chronological puzzles. Dust is everywhere in the modern universe. It fills the space between stars and galaxies, absorbs ultraviolet and visible light, and re-radiates it as infrared, shapes the colours of galaxies we observe, and provides the raw material from which planets form. When you look at images of spectacular nebulae like the Eagle Nebula's pillars of creation, those dark silhouettes are sculpted by dust. When you observe distant galaxies, the dust within them affects their appearance, dimming their light and reddening their colours. But dust doesn't exist at the beginning. In the moments after the Big Bang, the universe contained only the lightest elements: hydrogen, helium, and trace amounts of lithium. Everything else, all the heavier elements that make up dust, had to be created later, forged in the nuclear furnaces of stars and dispersed into space when those stars died. This process takes time. Stars live for millions to billions of years depending on their mass, with massive stars living fast and dying young in spectacular supernova explosions that seed their surroundings with newly formed heavy elements. These elements, ejected at high speeds, mix with the surrounding gas, gradually enriching it with the building blocks of dust. Over time, in cooler, denser regions, atoms of carbon, silicon, and other elements stick together, forming microscopic grains that we call dust. The standard model of cosmic chemical evolution predicted that significant amounts of dust shouldn't appear until the universe was at least several 100 million years old, perhaps closer to 1 billion years, after enough generations of stars had lived and died to produce substantial quantities of heavy elements. Early galaxies should be relatively dust-poor, showing bluer colours and less infrared emission than mature galaxies. Webb has found otherwise. Many of the early galaxies observed at high redshift show clear evidence of substantial dust. Their infrared emission is strong, indicating they contain dust that's absorbing starlight and re-radiating it at longer wavelengths. Their colours are redder than would be expected for dust-free galaxies. Spectroscopic observations detect absorption, features characteristic of various dust components. Some of these dusty galaxies are observed at redshifts around 10 to 11, when the universe was only 400 to 500 million years old. The presence of dust at these epochs suggests that multiple generations of stars had already formed, lived, and died, enriching the interstellar medium with heavy elements that subsequently formed dust grains. But how many generations? Consider the life cycle involved. The first stars form, perhaps at around 100 to 200 million years after the Big Bang. Massive stars among this first generation live for a few million years before exploding as supernovae. Their ejecta mix with surrounding gas. A second generation of stars forms from this enriched gas, perhaps 50 to 100 million years later. Some of these stars are also massive and short-lived, contributing additional heavy elements when they die. After this second generation, the heavy element abundance might be sufficient for significant dust formation. Adding these timescales together, you need at least 100 to 200 million years of stellar evolution to produce observable amounts of dust, and this must happen before the epoch when we're observing these dusty galaxies. If we're seeing dust at redshift 10, corresponding to about 470 million years after the Big Bang, then substantial star formation and chemical enrichment must have occurred by at most 300 million years after the Big Bang, requiring star formation to begin even earlier, perhaps as early as 100 million years after the Big Bang. This compresses the timeline uncomfortably. It means the first stars, the first galaxies, and multiple generations of stellar evolution all had to occur in a narrow window of time, much narrower than standard models predicted. Every process has to happen faster, more efficiently than we thought possible. There's also the question of where the star formation occurred. If the dust we observe accumulated over multiple generations of stars, then these early galaxies must have sustained vigorous star formation for hundreds of millions of years. But what was fueling this star formation? Where was the gas coming from? How was it being replenished faster than stars could consume it? Some astronomers have proposed that the early universe might have been more efficient at forming dust than we realise. Perhaps dust can form more quickly than standard models assume, assembling directly in the ejecta of supernovae or in the cool. Dense winds from evolved stars. Perhaps the conditions in the early universe, with different gas temperatures and densities than later epochs, somehow favoured rapid dust production. Others suggest that the dust might be telling us about a more vigorous and earlier onset of star formation than any model currently predicts, pushing the cosmic dawn back even further into the first 100 million years after the Big Bang. An era where our understanding becomes increasingly speculative. The dust in these early galaxies represents more than just a chemical curiosity. It's a timeline written in microscopic particles, each grain a tiny archive of stellar death and chemical evolution, and the presence of these archives so early in cosmic history suggests that the story of the universe's first few 100 million years was far more active, far more dramatic than we previously imagined. When astronomers analyse the light from distant galaxies, they're essentially conducting cosmic archaeology, reading the stellar populations like layers in an excavation site. The spectrum of a galaxy, the way its light is distributed across different wavelengths, contains information about what kinds of stars it contains, how old those stars are, and how the galaxy has evolved over time. And among Webb's impossible galaxies, the stellar populations present puzzles that deepen the mystery. Stars come in different varieties. Massive young stars shine brilliantly in blue and ultraviolet light, burning their fuel quickly and dominating the light from galaxies with active star formation. Intermediate mass stars like our Sun emit mostly invisible wavelengths and live for billions to tens of billions of years. Low-mass red dwarf stars shine faintly in red and infrared, but they're incredibly long-lived, capable of burning for hundreds of billions of years, longer than the current age of the universe. When you look at a galaxy's combined light, you're seeing the summed emission from all its stars, and this combined spectrum tells you about the galaxy's stellar population. A galaxy dominated by young, massive stars will appear blue and will show strong emission lines from ionized gas, signatures of vigorous ongoing star formation. A galaxy containing mostly old stars will appear redder, with absorption features indicating the presence of cool stellar atmospheres and lacking the bright emission lines of star-forming regions. Several of Webb's early galaxies show spectral characteristics indicating they contain old stellar populations, stars that formed hundreds of millions of years before the epoch when we're observing the galaxy. Finding old stars in galaxies observed at redshift 10 or 11 is profoundly strange, because it implies that star formation began even earlier than the observed galaxy's age. Consider a galaxy observed at redshift 11, corresponding to about 420 million years after the Big Bang. If this galaxy shows evidence of stars that are 300 million years old, then those stars must have formed just 120 million years after the Big Bang, deep in what should have been the cosmic dark ages, possibly before the first stars are thought to have ignited. The evidence for old stellar populations comes from several spectral features. Certain absorption lines, particularly from elements like carbon and oxygen, are stronger in the spectra of cool, evolved stars than in young hot stars. The overall shape of the spectrum, the way light is distributed across wavelengths, also provides clues. Galaxies with significant populations of old stars show what astronomers call a Balmer break, a distinctive drop in the spectrum's intensity at specific wavelengths caused by hydrogen absorption in stellar atmospheres, and this feature is more pronounced when old stars dominate the light. Some of the early galaxies Webb has observed show clear Balmer breaks and other signatures of old populations, suggesting they contain stars formed hundreds of millions of years before the observation epoch. This pushes star formation back to incredibly early times when our models struggle to produce stars efficiently. There's another complicating factor related to something called population 3 stars. These were the hypothetical first generation of stars formed from primordial hydrogen and helium before any heavy elements existed. Population 3 stars should have been very different from stars today, extremely massive and hot, living only a few million years before exploding in powerful supernovae that enriched the universe with its first heavy elements. These first stars should have produced a characteristic signature in the light from early galaxies, a signature that's largely absent in most of Webb's observations. The lack of clear population 3 signatures suggests that by the time we're observing these early galaxies, multiple generations of stars had already formed, lived and died, and the galaxies had already transitioned to forming what are called population 2 stars, which are enriched with at least small amounts of heavy elements. This transition should take time, perhaps 100 to 200 million years, yet it appears to have occurred very early in cosmic history. Some galaxies show mixed populations with both young, actively forming stars and older stellar populations coexisting. This indicates episodic star formation, periods of intense activity followed by quiescence, followed by renewed activity. Understanding what drives these episodes is another challenge. In nearby galaxies, episodic star formation is often triggered by galaxy mergers or interactions, but in the early universe, galaxies were more widely separated, and mergers should have been relatively rare. The stellar mass-to-light ratios of these early galaxies also present difficulties. Mass-to-light ratio measures how much stellar mass exists relative to the light the galaxy emits, and this ratio depends on the stellar population's age and composition. Young stellar populations have low mass-to-light ratios because massive bright stars dominate the light output. Old populations have higher ratios because the massive stars have died, leaving behind less luminous but still massive remnants. Several early galaxies show mass-to-light ratios suggesting old populations, which again implies extended star formation histories beginning very early. But when you calculate the total stellar mass implied by these ratios, you often get values that are difficult to reconcile with theoretical models of how quickly stars can form from available gas. All these stellar population puzzles point toward a consistent theme that the early universe was far more active, far more evolved, far more mature than we expected, as if the cosmic clock was running faster in those first few 100 million years, cramming processes that should take 1 billion years into a fraction of that time. Among the many surprising characteristics of Webb's impossible galaxies, perhaps none is more visually striking than their morphologies, their shapes and structures, which appear far too organised and complex for such young cosmic citizens. When astronomers began systematically studying galaxies in the early 20th century, they developed classification schemes to categorise the diverse forms they observed. Edwin Hubble's famous tuning fork diagram divided galaxies into ellipticals, which are smooth and featureless, and spirals, which show distinct disk structures with graceful spiral arms. Later additions included irregular galaxies, which lack organised structure, and peculiar galaxies, which show evidence of recent interactions or mergers. This classification wasn't just descriptive, it was thought to represent an evolutionary sequence. The prevailing assumption was that galaxies start irregular and chaotic, gradually becoming more organised through dynamical processes over hundreds of millions to billions of years. Spiral structures, for instance, are thought to form through density waves propagating through galactic disks, processes that require the disk to be stable and relatively undisturbed for extended periods. Bars, those linear structures extending from many galaxies' centres, form through gravitational instabilities and interactions, again requiring time to develop. Early galaxies, observed when the universe was young, should therefore appear irregular and chaotic, showing little organised structure. This expectation was largely confirmed by Hubble Space Telescope observations of galaxies at moderate redshifts, between 2 and 6, corresponding to the universe between about 1 and 3 billion years old. Those galaxies indeed looked more irregular, more disturbed, less organised than nearby galaxies, fitting the narrative of gradual structure formation. Webb has challenged this narrative. several galaxies observed at redshifts between 8 and 12, when the universe was only 300 to 600 million years old, show surprisingly organised structures. Some display clear disk components, flattened rotating structures that should take time to form as gas settles into a galaxy's gravitational potential well. Others show evidence of central bulges, dense concentrations of stars at galaxies' centres that typically form through mergers or through the migration of gas toward the centre, driven by bars or other non-axisymmetric features. Most strikingly, some early galaxies show what appear to be bar structures, those linear features that indicate dynamical evolution and gravitational instabilities. Bars shouldn't form in very young galaxies because they require the galactic disk to be massive enough and stable enough for gravitational instabilities to amplify non-circular motions into organised patterns, and this process was thought to require at least 500 million to 1 billion years. One particularly well-studied example is a galaxy observed at redshift 9.1, when the universe was about 540 million years old, that shows clear evidence of a rotating disk with what appears to be a central bar. The rotation curve, measured through spectroscopic observations of how gas and stars move at different distances from the galaxy's centre, indicates a well-organised structure with orderly rotation rather than chaotic random motions. These morphological findings connect to broader questions about galaxy formation mechanisms. In the hierarchical merging model, galaxies grow through countless mergers of smaller systems, and this merger-driven growth should produce irregular, disturbed morphologies, at least until the galaxy has time to settle and reorganize after mergers. The presence of organized structures in early galaxies suggests either that mergers were less important than thought, or that galaxies can organize themselves more quickly after mergers, or that some early galaxies grew through smooth accretion of gas rather than violent mergers. There's also the question of angular momentum, the measure of how much rotation a system has. When gas collapses to form a galaxy, it retains angular momentum, which causes it to spin. The amount of angular momentum determines how extended and flat the resulting disk will be. Too much angular momentum and the disk becomes too extended and unstable. Too little, and the gas falls directly to the centre without forming a disk. Understanding how galaxies regulate their angular momentum during formation is crucial to explaining their final structures. Early galaxies showing well-defined disks must have managed their angular momentum precisely, retaining enough to form extended rotating structures, but not so much that they flew apart. This suggests sophisticated feedback processes were operating, perhaps involving outflows driven by supernovae or active galactic nuclei that remove gas with specific angular momentum distributions, sculpting the galaxy's structure. Some researchers have proposed that the early universe's higher gas densities might have enabled faster structure formation. With more gas available in smaller volumes, gravitational instabilities could amplify more quickly, allowing organised structures to emerge sooner. Others suggest that the dark matter halos hosting early galaxies might have different properties than later halos, affecting how gas settles within them. There's also speculation about whether our understanding of dynamical timescales is incomplete. Perhaps processes we think take hundreds of millions of years can actually occur faster under the specific conditions of the early universe, with higher gas densities, different temperature distributions, and more vigorous feedback than later epochs. What these morphological observations reveal, ultimately, is that the path from chaos to order in the universe is less straightforward than we imagined, that complexity can emerge more quickly than our models predicted, and that the early universe was sculpting beauty and structure while it was still, by cosmic standards, barely born. The discoveries Webb has made about early galaxies don't just challenge our understanding of galaxy formation. They ripple backward through cosmic history to question even earlier events, including cosmic inflation, that incredibly brief but crucial period in the universe's first fraction of a second that set the initial conditions for everything that followed. Cosmic inflation is one of modern cosmology's most successful theories, despite describing events so early and so brief that they seem almost impossible to verify. The theory proposes that in the first tiny fraction of a second after the Big Bang, perhaps at around 10 to the negative 35 seconds, the universe underwent a period of exponential expansion, growing by a factor of at least 10 to the 26 in less time than it takes light to cross an atomic nucleus. This inflationary epoch solved several long-standing cosmological puzzles. It explained why the universe appears so flat, why it looks nearly the same in all directions, and crucially for our purposes, where the initial density fluctuations came from, those tiny variations that would eventually grow into galaxies and large-scale structure. During inflation, quantum fluctuations in the fabric of space-time itself got stretched to cosmic scales, imprinted as density variations that were nearly, but not quite, perfectly uniform. The properties of these initial fluctuations, their amplitude and statistical characteristics, are precisely predicted by different inflationary models, and can be measured by observing the cosmic microwave background radiation. The Planck satellite and other experiments have mapped these fluctuations with exquisite precision, confirming that they match inflationary predictions remarkably well. This agreement is one of the pillars supporting our confidence in the standard cosmological model, but here's where Webb's discoveries create tension. The amplitude and distribution of the initial fluctuations determine how quickly structure can form through gravitational collapse. If the fluctuations are too small, structure formation proceeds very slowly, and you struggle to build galaxies quickly enough. If they're too large, structure forms too efficiently, producing too many massive objects too early. Current measurements of the cosmic microwave background indicate the fluctuations have an amplitude of about 1 part in 100,000, a specific value that's been measured with about 1% precision. This amplitude, combined with the known properties of dark matter and the expansion rate of the universe, feeds into simulations that predict how structure should evolve over cosmic time, and those predictions don't match what Webb observes in terms of early massive galaxy abundance. One way to reconcile this tension is to propose that inflation produced a different statistical distribution of fluctuations than standard models predict. Perhaps there was more power on small scales, more strong fluctuations in small regions, which would provide extra seeds for early galaxy formation. Such modifications to the inflationary spectrum need to be subtle enough that they don't conflict with cosmic microwave background observations, which tightly constrain the large-scale properties, while still affecting small-scale structure formation. Another possibility involves the specific mechanism driving inflation. Different inflationary models, based on different assumptions about the quantum fields responsible for inflation, produce slightly different predictions for the fluctuation spectrum. Some models, particularly those involving multiple scalar fields or more complex potentials, can produce enhanced fluctuations on certain scales while remaining consistent with observations on others. There's also the intriguing possibility of primordial non-Gaussianity, a technical term describing deviations from a perfectly random distribution of fluctuations. Standard inflation predicts fluctuations should be Gaussian, meaning they follow the familiar bell curve distribution. But some inflationary models produce non-Gaussian fluctuations, where rare, unusually strong fluctuations occur more frequently than a Gaussian distribution would predict. These rare, strong fluctuations could seed the earliest massive galaxies without affecting the average fluctuation amplitude that cosmic microwave background experiments measure. Primordial black holes represent another exotic possibility connected to inflation. If inflation produced rare, extremely strong fluctuations in small regions, these regions might have collapsed directly into black holes shortly after the Big Bang, creating primordial black holes that could serve as seeds for the supermassive black holes Webb has found in early galaxies. This would elegantly solve the black hole seed problem we discussed earlier, though creating primordial black holes with the right masses and abundances requires very specific inflationary conditions. What makes these discussions both fascinating and challenging is how they connect observations of galaxies billions of light-years away to events that occurred in the first inconceivably brief moments of cosmic time. The density fluctuations that inflation imprinted 13.8 billion years ago directly influenced which regions would form galaxies early and which would form them late, creating a causal chain linking the universe's first fraction of a second to the galaxies Webb observes today. Revising our understanding of inflation isn't undertaken lightly. The theory has been successful across multiple observational tests, from the cosmic microwave background to the distribution of galaxies to gravitational wave backgrounds. Any modification needs to preserve these successes while explaining the new observations. This is the nature of scientific progress, not discarding successful theories at the first sign of new data, but carefully exploring whether the theories can be refined to accommodate new discoveries while maintaining consistency with established observations. The question remains open, debated in conferences and explored in countless research papers, whether inflation's final chapter has been written, or whether Webb's impossible galaxies are telling us that even our understanding of the universe's first moments needs revision. At the heart of the impossible galaxy problem lies a deceptively simple question that astronomers have been grappling with for decades, one that Webb's discoveries have brought into sharp focus with new urgency. How efficiently does gas turn into stars? And was this efficiency different in the early universe? Star formation is, in principle, straightforward. You start with a cloud of gas, mostly hydrogen with some helium. Gravity pulls the gas together, compressing it. As the gas compresses, it heats up, and this heat creates pressure that resists further compression. For star formation to proceed, the gas must lose this heat energy by radiating it away, cooling down so that gravity can overcome the pressure and continue the collapse. Eventually, the densest regions become hot enough for nuclear fusion to ignite, and stars are born. But converting this simple principle into quantitative predictions about how many stars form in a given environment and over a given time is extraordinarily difficult. The process depends on countless factors: the gas temperature, density, chemical composition, magnetic field strength, turbulence, rotation, the radiation from nearby stars that can heat or ionize the gas, shocks from supernovae that can trigger or disrupt collapse, and more. Each factor affects the others in nonlinear ways, creating a web of interdependencies that challenges both theoretical understanding and computational simulation. Astronomers quantify star formation using something called the star formation efficiency, which measures what fraction of available gas actually turns into stars over a given time period. Observations of nearby galaxies and star-forming regions in the Milky Way suggest typical efficiencies of a few percent to perhaps 10%. This means that out of all the gas in a galaxy that could potentially form stars, only a small fraction actually does, with the rest either heated by stellar feedback, expelled by galactic winds, or simply remaining as diffuse gas that never becomes dense enough to collapse. This relatively low efficiency is crucial for explaining the observed properties of galaxies. If star formation were too efficient, if most of a galaxy's gas quickly turned into stars, you'd rapidly exhaust the fuel supply, and galaxies would stop forming stars far earlier than observed. The fact that galaxies continue forming stars over billions of years, steadily converting gas into stars at measured rates, implies that star formation is a regulated process, with feedback mechanisms preventing runaway collapse. But here's the problem Webb has highlighted. The massive galaxies observed in the early universe appear to have converted gas into stars far more efficiently than models predict. To build a galaxy containing 10 billion solar masses of stars by the time the universe is 500 million years old requires either enormous amounts of gas concentrated in a small region, or much higher star formation efficiency than observed in nearby galaxies, or both. Let's consider the numbers. If you have a dark matter halo that can gravitationally capture a certain amount of gas, and you assume star formation proceeds at the typical few percent efficiency observed locally, you can calculate how much stellar mass should accumulate over a given time. For the massive early galaxies Webb has found, doing this calculation with standard assumptions produces stellar masses far below what's observed. The galaxies are too massive by factors of 5 to 10, implying either that they had access to far more gas than models predict, or that they converted that gas into stars far more efficiently. Some researchers have proposed that star formation efficiency might have been genuinely higher in the early universe. The gas at early times had different properties. It was hotter on average, denser in regions that would form galaxies, and metal-poor, lacking the heavy elements that in later epochs provide important cooling pathways. Perhaps these different conditions favoured more efficient star formation, allowing larger fractions of available gas to collapse into stars. There's some theoretical support for this idea. Metal-poor gas can only cool through a limited set of processes, primarily through emission from hydrogen and helium atoms. Once the gas cools to a certain temperature, these cooling processes become inefficient, and the gas can fragment into clumps more readily without further cooling, potentially forming stars more efficiently. In contrast, metal-rich gas can cool to lower temperatures through emission from metal atoms and molecules, fragmenting into smaller clumps that might form lower-mass stars less efficiently. Another factor involves something called top-heavy initial mass functions. When stars form, they don't all have the same mass. Instead, they're distributed according to what's called the initial mass function, with many low-mass stars and progressively fewer high-mass stars. In nearby star-forming regions, for every star like the Sun that forms, roughly 1 or 200 stars with 1/10 the Sun's mass also form. This distribution affects the total light a stellar population produces and how quickly it exhausts its gas supply. Some theorists have suggested that in the early universe, the initial mass function might have been top-heavy, meaning it produced proportionally more high-mass stars and fewer low-mass stars. High-mass stars are far more luminous than low-mass ones, so a top-heavy initial mass function would make galaxies appear brighter and more massive for a given amount of gas converted to stars. It would also mean more rapid chemical enrichment and faster feedback effects, as high-mass stars die young in supernova explosions. However, a top-heavy initial mass function creates other problems. High-mass stars die quickly, so galaxies with top-heavy initial mass functions would exhaust their stellar populations rapidly, leaving behind many stellar remnants like neutron stars and black holes, but few visible stars. The detailed spectral characteristics of early galaxies don't always support this scenario, suggesting that at least some early galaxies had initial mass functions similar to those observed today. Gas accretion rates present another piece of the puzzle. Galaxies don't form in isolation. They continuously accrete gas from the surrounding intergalactic medium, particularly through streams of cold gas that flow along dark matter filaments into galaxy halos. In the early universe, when everything was denser and closer together, these accretion rates might have been higher, providing a larger fuel supply for star formation. Simulations of early galaxy formation suggest that gas accretion could indeed have been more vigorous in the first billion years after the Big Bang, with gas streaming into galaxies at rates of tens to hundreds of solar masses per year, rates sufficient to sustain the high star formation rates Webb observes. But even with higher accretion rates, you still need efficient star formation to convert that inflowing gas into stars before feedback processes heat or expel it. This brings us back to the central mystery. Something about star formation in the early universe appears to have worked differently than it does today, either through fundamentally different efficiencies, different initial mass functions, different feedback regulation, or some combination of all these factors, and understanding what that something was remains one of the most pressing questions in contemporary astrophysics. Star formation doesn't occur in a vacuum, unaffected by the stars themselves. Once stars begin to shine, they dramatically alter their environment through processes astronomers collectively call feedback, and understanding how feedback regulated or failed to regulate star formation in the early universe is crucial to explaining Webb's impossible galaxies. Feedback operates through multiple channels, each affecting gas in different ways. The most obvious is radiation. Stars, particularly massive young ones, emit intense ultraviolet light that heats surrounding gas and ionizes it, stripping electrons from atoms. This heating increases gas pressure, which can counteract gravity and prevent further collapse. In extreme cases, radiation pressure from intense starlight can drive winds of gas away from the galaxy entirely, removing the fuel needed for future star formation. Cosmic rays, high-energy particles accelerated by supernovae and other energetic events, represent another feedback channel that's been less studied in the context of early galaxies. Cosmic rays can heat gas and provide additional pressure support against gravitational collapse, potentially affecting star formation regulation. In the early universe, with more frequent supernovae from high star formation rates, cosmic ray pressure might have been more important than in modern galaxies. Active galactic nuclei feedback, driven by supermassive black holes at galaxy centers, adds another layer of complexity. As black holes accrete matter, they release enormous amounts of energy, often in the form of powerful jets and winds that can heat or expel gas from the entire galaxy. The early supermassive black holes Webb has discovered would have been producing such feedback, potentially affecting their host galaxy's star formation. Interestingly, there's a balance to strike with black hole feedback. Too weak, and it doesn't regulate star formation, allowing galaxies to grow too massive. Too strong, and it quenches star formation entirely, preventing galaxy growth. Observations of nearby galaxies suggest this balance is finely tuned, with black hole masses correlating closely with the masses of their host galaxies' central bulges, implying a coevolution regulated by feedback. The timing of feedback is also critical. Feedback that occurs continuously and gently might have different effects than feedback that occurs in the intense bursts, separated by quiet periods. Continuous feedback might maintain the gas in a heated state, preventing star formation, while bursty feedback might allow gas to cool and collapse between bursts, permitting episodic star formation. What Webb's observations suggest is that in the early universe, despite intense feedback from vigorous star formation and active black holes, galaxies somehow maintained access to sufficient gas supplies and managed star formation in ways that built massive stellar populations in remarkably short times, revealing that the balance between gas supply, star formation, and feedback was different than in later cosmic epochs. When faced with observations that challenge fundamental assumptions, scientists must consider not just modifications to specific processes, but whether the broader framework itself might need revision. Webb's impossible galaxies have prompted some researchers to question the lambda CDM cosmological model itself, exploring whether alternative cosmologies might better explain the observations. Perhaps the most radical alternative questions whether the Big Bang cosmological framework itself needs revision. Steady-state cosmology, once a serious competitor to Big Bang theory, but largely abandoned after the discovery of the cosmic microwave background, proposed that the universe has always existed in roughly its current state, with continuous creation of matter balancing the dilution from expansion. While steady-state cosmology in its original form contradicts too many observations to be viable, some researchers have explored whether elements of it might be incorporated into more sophisticated frameworks. Cyclic cosmologies represent another exotic alternative, proposing that the universe undergoes endless cycles of expansion and contraction, with each cycle potentially seeding the initial conditions for the next. In such frameworks, the structures we observe might have originated in previous cycles, allowing more time for their formation than the 13.8 billion years since our cycle's Big Bang. However, cyclic cosmologies face serious theoretical challenges, particularly explaining how information could survive the transition between cycles, and why we don't observe remnants from previous cycles. What's important to understand is that these alternative cosmologies remain speculative, explored by small numbers of researchers, while the vast majority of the astronomical community continues working within the lambda CDM framework, trying to refine specific processes like star formation efficiency or dark matter clustering rather than abandoning the entire model. This isn't dogmatism or resistance to new ideas. It's a reasoned approach based on the reality that lambda CDM has successfully explained so many diverse observations that replacing it requires not just explaining Webb's galaxies, but maintaining consistency with everything else we've learned about the universe. The scientific method requires that extraordinary claims require extraordinary evidence, and while Webb's discoveries are certainly surprising, they haven't yet risen to the level that would justify abandoning a cosmological framework that's been validated across decades of observations and multiple independent measurement techniques. Still, these alternative explorations serve an important purpose, pushing the boundaries of theoretical thinking, ensuring that no possibility remains unexamined, and occasionally revealing insights that can be incorporated back into the standard framework, even if the full alternative theory isn't adopted. Computer simulations have become indispensable tools for understanding cosmic structure formation, allowing astronomers to evolve the universe from its initial conditions through billions of years of gravitational collapse, gas dynamics, star formation, and feedback in ways that no analytical calculation can match. And in the wake of Webb's discoveries, enormous computational effort has gone into simulating the early universe to understand whether adjustments to simulation parameters can reproduce the observed populations of massive early galaxies. One intriguing result from recent simulations involves something called direct collapse gas flows. In some simulations, gas doesn't gradually accumulate in galaxies through steady accretion, but instead flows in rapidly during brief episodes of intense accretion, potentially dumping enormous amounts of gas into galaxies over relatively short periods. These accretion episodes might be triggered by galaxy interactions, or by the configuration of surrounding dark matter structure, and could provide the large gas reservoirs needed to form massive galaxies quickly. The black hole seed problem has also been addressed through simulations, with some successfully producing massive black holes at early times through direct collapse of pristine gas clouds, or through super Eddington accretion onto stellar mass black hole seeds. These simulations require specific conditions, particularly gas clouds that remain metal-free and that avoid fragmenting into stars, but they demonstrate pathways that might explain the supermassive black holes Webb has found. What's emerged from this intensive simulation effort is a more nuanced picture. The standard lambda-CDM cosmology probably doesn't need to be abandoned entirely, but our implementation of the detailed baryonic physics, the processes involving ordinary matter that form stars and galaxies, likely needs refinement. The early universe probably was more efficient at forming stars, probably did experience more vigorous gas accretion, and probably had feedback that operated somewhat differently than in later epochs. The challenge now is translating these simulation insights into physical understanding. Not just finding parameter combinations that match observations, but understanding the underlying physics that would produce those parameter values, transforming simulation results from numerical experiments into genuine theoretical insights about how the universe works. As Webb continues its mission, collecting ever more data from the early universe, each new observation cycle brings both clarity and additional complexity to the puzzle of the impossible galaxies, revealing layers of detail that earlier observations couldn't access and raising questions that astronomers are only beginning to formulate. One of Webb's particular strengths is spectroscopy. The ability to split light into its component wavelengths and measure the precise spectrum of individual galaxies. Unlike imaging, which gives a galaxy's overall appearance and approximate brightness, spectroscopy reveals chemical compositions, measures precise redshifts, identifies emission and absorption features from specific atomic transitions, and provides detailed information about physical conditions within the galaxy. Throughout 2023 and 2024, spectroscopic surveys with Webb have been systematically measuring detailed spectra for hundreds of high redshift galaxies, and these spectra are revealing unexpected complexity. Many early galaxies show emission lines indicating vigorous ongoing star formation, with ionized oxygen, hydrogen, and other elements producing characteristic spectral signatures. But the strengths of these emission lines, the ratios between different elements, and their velocities provide information about the intensity of star formation, the hardness of the radiation field, and the kinematics of gas within the galaxies. Some galaxies show extremely strong emission lines, stronger than typically observed in later galaxies forming stars at similar rates. This might indicate that early galaxies had different conditions in their star-forming regions, perhaps with lower metal abundances that affect how gas cools and emits radiation, or it might suggest that early stars produced harder, more energetic radiation that ionized surrounding gas more intensely. The velocities measured from spectral lines reveal how gas moves within galaxies. In some early galaxies, gas shows ordered rotation, indicating settled disk structures. In others, gas moves chaotically, suggesting either very turbulent environments or galaxies caught in the process of merging. These kinematic measurements provide crucial constraints on galaxy masses, with rotation speeds depending on the gravitational pull from all the matter, both visible and dark. Interestingly, several early galaxies show velocity dispersions, measures of random gas motions that are remarkably high, suggesting extremely turbulent conditions or perhaps indicating that we're observing major mergers in progress. Understanding what drives this turbulence, whether it's feedback from star formation, accretion of gas from outside, or gravitational interactions, remains an active area of investigation. Chemical abundance measurements from spectroscopy have provided another surprise. The ratio of oxygen to hydrogen, which astronomers use as a proxy for overall heavy element enrichment, varies significantly among early galaxies. Some show abundances approaching 1/10 of solar values, implying substantial chemical evolution, while others show much lower abundances, closer to the primordial values from Big Bang nucleosynthesis. This variation suggests diverse star formation histories. Galaxies with higher metal abundances must have formed and destroyed multiple generations of stars, enriching their gas over extended periods. Those with lower abundances might be experiencing their first major burst of star formation, or they might have been continually diluting their enriched gas through accretion of pristine gas from the intergalactic medium. One particularly intriguing discovery involves nitrogen. Nitrogen is produced primarily in intermediate mass stars through specific nuclear reactions, and in the modern universe, nitrogen abundance relative to oxygen provides information about a galaxy's star formation history. But several early galaxies show unexpectedly high nitrogen abundances, suggesting either that nitrogen production was more efficient in early stellar populations, or that intermediate mass stars evolved more quickly in the early universe than current models predict. Webb has also been observing early galaxies in multiple filters, measuring their brightnesses at different infrared wavelengths. These multi-wavelength observations constrain the galaxy's stellar populations, dust content, and star formation histories. Some galaxies appear very red in these observations, indicating either significant dust obscuration or the presence of old stellar populations, while others appear blue, consistent with vigorous ongoing star formation with minimal dust. The red galaxies are particularly puzzling because dust implies chemical enrichment and multiple stellar generations, requiring extended star formation histories. Yet these red dusty galaxies exist at redshifts suggesting the universe was only 400 to 500 million years old, leaving limited time for the dust production and stellar aging that produce red colours. Gravitational lensing observations have added another dimension to the picture. When massive galaxy clusters sit between Webb and more distant galaxies, the cluster's gravity bends and magnifies the light from background galaxies, sometimes making faint distant galaxies visible that would otherwise be too faint to detect. Several Webb programs have exploited this cosmic magnification to observe extremely faint early galaxies, reaching down to lower masses than possible in unlensed fields. These lensed observations reveal populations of smaller galaxies at high redshift, closer to the dwarf galaxies that hierarchical models predict should be common in the early universe. However, even some of these smaller galaxies appear to be forming stars more vigorously and contain more mass than models predicted, suggesting that the tension between observations and theory extends across the full range of galaxy masses, not just the most extreme massive examples. Each new observation refines our understanding, but also introduces new questions, revealing that the early universe was even more complex, even more diverse, even more active than we initially recognized from the first shocking discoveries. Among the various attempts to reconcile Webb's observations with theoretical expectations, one question that's been carefully examined is whether the redshift measurements themselves might somehow be mistaken, whether the galaxies might not actually be as distant and as early as they appear. Redshift is the cornerstone of cosmic distance measurement for objects beyond our local group of galaxies. It's based on a simple principle. As the universe expands, the wavelength of light travelling through space gets stretched, shifting spectral features toward longer, redder wavelengths. By measuring how much a galaxy's spectral features have been shifted relative to their laboratory rest wavelengths, we can determine the redshift, which in turn tells us the galaxy's distance and the cosmic epoch when the light was emitted. For decades, redshift measurements have been the reliable foundation of observational cosmology, confirmed through countless observations and cross-checks. When astronomers measure a galaxy's redshift spectroscopically, identifying characteristic patterns of emission or absorption lines and measuring their wavelength shifts, the results are generally unambiguous and precise. However, for the most distant galaxies, particularly those at redshifts above 10, spectroscopic confirmation becomes challenging because these galaxies are faint and their spectral features shift into the infrared where Earth's atmosphere is opaque, requiring space-based observations. Before Webb, many high redshift galaxy candidates were identified using photometric redshifts, which estimate redshift based on a galaxy's brightness in multiple filters, rather than from spectroscopy. Photometric redshifts are less precise than spectroscopic ones, and can occasionally be wrong, particularly if a galaxy has unusual colours or properties. One way to get a misleadingly high photometric redshift is if a galaxy contains dust that absorbs blue light, making the galaxy appear redder than it actually is, mimicking the reddening caused by redshift. In such cases, a dusty galaxy at moderate redshift might be mistaken for a dust-free galaxy at high redshift. When Webb's first images revealed numerous high redshift galaxy candidates based on photometric redshifts, some skeptics wondered whether a significant fraction might be dusty interlopers at lower redshifts rather than genuinely early galaxies. This was a reasonable concern that required systematic spectroscopic follow-up to resolve. By now, many of Webb's high redshift galaxies have been confirmed spectroscopically, with clear detections of emission lines at the predicted redshifted wavelengths, leaving no ambiguity about their distances. For these confirmed galaxies, there's no question they're genuinely at high redshift, genuinely in the early universe. The impossible galaxy problem is real for these objects, not an artifact of redshift errors. That said, some of the initial highest redshift candidates, particularly those claiming redshifts above 15, have turned out upon spectroscopic follow-up to be at somewhat lower redshifts, typically around 4 to 6. These corrections highlight the limitations of photometric redshifts for extreme objects, but crucially, even the revised redshifts still place these galaxies in the relatively early universe, and they remain more massive and more mature than models comfortably predict for their epochs. There's another subtle way redshift could potentially be misleading, though it's highly speculative. Standard cosmology assumes that redshift is caused purely by cosmic expansion, the stretching of space as the universe grows. But if there were additional contributions to redshift from other effects, like gravitational redshift from extremely deep gravitational potentials or Doppler shifts from peculiar velocities, these could slightly alter the interpretation of measured redshifts. Peculiar velocities, the motions of galaxies relative to the smooth Hubble expansion, do contribute to observed redshifts, but these contributions are typically small, corresponding to velocity shifts of a few hundred kilometers per second, compared to recession velocities of hundreds of thousands of kilometers per second for high redshift galaxies. Even accounting for peculiar velocities, the redshifts of Webb's galaxies clearly indicate they're in the early universe. Gravitational redshift, the shift in photon wavelengths caused by climbing out of gravitational potential wells, is another theoretical contribution, but for normal galaxies this effect is tiny compared to cosmological redshift. Only in the most extreme gravitational environments, like near black hole event horizons, does gravitational redshift become significant, and those conditions don't apply to the galaxies Webb is observing. Some alternative cosmological models propose that redshift might have contributions from mechanisms other than expansion, like tired light theories that suggest photons lose energy as they travel through space. However, these theories have been thoroughly ruled out by multiple observations, including the time dilation of supernova-like curves at different redshifts, the temperature evolution of the cosmic microwave background, and the detailed patterns of galaxy clustering, all of which confirm that redshift is caused by cosmic expansion exactly as standard cosmology predicts. What we can say with confidence is that the redshift measurements are fundamentally sound. The galaxies Webb has observed are genuinely at the distances and epochs their redshifts indicate. This isn't a measurement error or an interpretation mistake. The early universe genuinely produced massive evolved galaxies earlier than our models predicted, and understanding how requires confronting the physics of galaxy formation, not questioning the reliability of redshift as a distance indicator. This doesn't mean every aspect of the observations is perfectly understood, or that no uncertainties remain, but the core puzzle of massive early galaxies is real, demanding explanation through improved theoretical understanding, rather than through skepticism about observational techniques. While Webb looks billions of light-years across the universe to observe early galaxies directly, another approach to understanding the early universe involves looking closer to home, studying the oldest stars in our own Milky Way galaxy and its satellites, stellar fossils that formed in the cosmic dawn and have survived to the present day. The Milky Way contains stars of many ages. Most stars, including our Sun, formed relatively recently in cosmic terms, within the last few billion years, from gas that had been enriched with heavy elements from previous stellar generations. But scattered throughout our galaxy, particularly in the halo surrounding the disk and in dwarf satellite galaxies orbiting the Milky Way, are stars that formed much earlier, some as far back as 13 billion years ago, when the universe was less than 1 billion years old. These ancient stars, often called population 2 or metal-poor stars because they contain very low abundances of heavy elements, preserve chemical signatures from the early universe. Their compositions reflect the gas from which they formed, which in turn reflects the nucleosynthesis from earlier stellar generations. By studying these ancient stars' chemical abundances in detail, astronomers can learn about the first stars and the conditions in early galaxies. One remarkable discovery involves what are called ultra-metal-poor stars, stars with iron abundances less than 1/10,000th of the Sun's. These stars must have formed from gas enriched by only a few earlier supernovae, possibly even by a single first-generation supernova. The specific patterns of elements in these stars, the ratios of carbon to iron, oxygen to magnesium, and other element pairs, provide clues about what kinds of stars exploded to produce the enrichment. The element ratios often differ from patterns seen in younger, more metal-rich stars, suggesting that the first stars indeed had different properties than later generations. Some ultra-metal-poor stars show unusual enhancements of carbon or other light elements, possibly indicating they formed from gas enriched by peculiar types of supernovae, or by massive stars that lost material through stellar winds before exploding. Another clue comes from studying the kinematics of ancient stars, their motions through the galaxy. Stars that formed in the same environment tend to move together, creating stellar streams and associations that can be identified even billions of years after formation. By tracing these associations, astronomers can identify groups of stars that formed together in early dwarf galaxies that were later accreted and absorbed by the growing Milky Way. Several such ancient stellar streams have been identified, each representing a dwarf galaxy that merged with the Milky Way billions of years ago. The stars in these streams all share similar chemical abundances and ages, providing snapshots of what small early galaxies were like. Interestingly, many of these ancient dwarf galaxy remnants contain stars with relatively low metal abundances, but show evidence of having experienced substantial star formation, forming millions to hundreds of millions of solar masses of stars before being absorbed by the Milky Way. This ties into the impossible galaxy problem in an interesting way. If dwarf galaxies in the early universe could form millions of solar masses of stars relatively quickly, and if many such dwarf galaxies existed, then mergers between multiple dwarfs could potentially build massive galaxies faster than models predict. The challenge is understanding whether enough dwarf galaxies existed and whether they merged frequently enough to explain Webb's observations. Globular clusters, those dense spherical collections of hundreds of thousands to millions of stars that orbit the Milky Way, provide another window into early galaxy formation. Many globular clusters are extremely old, with ages exceeding 12 billion years, and they likely formed in dwarf galaxies or protogalactic fragments that later merged to build the Milky Way. The chemical abundances in globular clusters tell complex stories. Many clusters show evidence of multiple stellar populations, with stars of the same age but different chemical compositions coexisting. This implies that star formation in early systems occurred in multiple episodes, with the first stellar generation enriching the cluster's gas, which then formed a second generation with different compositions. Understanding the timescales and mechanisms for this multi-generation formation might provide insights into early galaxy evolution. One particularly intriguing observation involves the age distribution of stars in the Milky Way's halo. Unlike the disk, which shows a wide range of stellar ages with ongoing star formation, the halo is dominated by very old stars, with ages clustered around 12 to 13 billion years. Very few halo stars have intermediate ages between 10 and 12 billion years old. This age gap suggests that the Milky Way's halo formation was rapid and early, assembling most of its stars within the first billion years after the Big Bang, then largely ceasing star formation as gas fell into the disk. This rapid, early assembly mirrors, on a smaller scale, what Webb observes in massive early galaxies. If the Milky Way's halo could form most of its stellar mass within the universe's first billion years, then perhaps other galaxies, in different environments or with different formation histories, could have been even more efficient, building massive stellar populations even faster. Studies of the Large and Small Magellanic Clouds, two dwarf galaxies orbiting the Milky Way, have revealed ancient stellar populations there as well, showing that even small galaxies experienced vigorous early star formation. The chemical patterns in these ancient stars suggest complex star formation histories, with multiple bursts of activity rather than smooth continuous star formation. What connects these local ancient stellar studies to Webb's distant galaxy observations is the recognition that early galaxy formation was diverse and vigorous across all mass scales, from dwarf galaxies to massive systems, and that the chemical and kinematic signatures from that era persist in stellar populations we can study in detail today, providing complementary evidence about the nature of the cosmic dawn. As we move deeper into our contemplation of Webb's impossible galaxies, it's worth pausing to acknowledge how much remains genuinely unknown, how many fundamental questions about the early universe still lack definitive answers, and how this uncertainty is not a failure of science, but rather its most honest and compelling edge. We still don't know what dark matter is. Despite decades of experiments, despite elaborate detection efforts deep underground and in space, despite the overwhelming gravitational evidence for its existence, dark matter's particle nature remains mysterious. We can map its distribution, measure its effects, constrain its properties, but we cannot say with certainty what it actually is, what fundamental particles compose the invisible mass that dominates cosmic structure formation. This uncertainty ripples forward into all our models of galaxy formation. If dark matter has properties we haven't accounted for, if it interacts in ways beyond gravity that we haven't detected, these hidden characteristics could affect structure formation in ways current models miss. The impossible galaxies might be revealing not just that our galaxy formation models are incomplete, but that our understanding of dark matter itself needs revision. We don't fully understand star formation. Even in nearby galaxies we can observe in detail. The process involves complex physics across enormous ranges of scale, from parsec-sized giant molecular clouds to sub-parsec-sized collapsing cores to the individual protostars that emerge from them. Magnetic fields, turbulence, radiation pressure, chemical processes all interact in nonlinear ways that make star formation difficult to predict from first principles. If we struggle to model star formation in well-observed nearby galaxies, how much more uncertain must our models be for distant early galaxies, where observations are limited and conditions were different? The initial mass function, that distribution of stellar masses formed from gas clouds, is assumed in most models to be universal. The same everywhere at all times. But we don't know if this assumption is correct. We can only directly measure the initial mass function in the solar neighbourhood and a few other nearby regions. Whether it was the same in the early universe, in different environments, at different metallicities, remains uncertain. And yet this function crucially affects predictions for galaxy properties, stellar feedback, chemical enrichment, everything. Our uncertainty here propagates through every calculation. We don't know how supermassive black holes form. The seed problem remains genuinely unsolved. We have proposed mechanisms, from stellar mass black holes growing through accretion and mergers to direct collapse of massive gas clouds to more exotic possibilities involving primordial black holes or dense stellar clusters. But we lack direct observational evidence confirming any of these pathways. The supermassive black holes Webb has found at high redshift highlight this gap in our understanding, showing us the consequences, the mature black holes, without revealing the origins we still struggle to explain. The role of magnetic fields in early galaxy formation is barely understood. Magnetic fields affect gas dynamics, provide pressure support against gravitational collapse, influence how gas cools and fragments, and regulate angular momentum transport. But magnetic fields in high redshift galaxies are almost impossible to observe directly, leaving their strengths and configurations largely unknown. Models either ignore magnetic fields or make simplistic assumptions about them, knowing these assumptions might be wrong but lacking observational constraints to improve them. We remain uncertain about the detailed history of cosmic reionization, that process by which the first stars and galaxies ionize the neutral hydrogen filling the universe. When did reionization begin? How long did it take? Was it driven primarily by massive stars and galaxies, or by quasars with supermassive black holes? How patchy was the process, with some regions ionizing early and others late? These questions matter because reionization affects the gas available for star formation, the clustering of galaxies, and the observability of early galaxies through the neutral hydrogen that absorbs their light. The relationship between galaxies and their dark matter halos, fundamental to all galaxy formation theory, involves numerous uncertainties. How efficiently does gas cool and fall into halos? How much is retained versus expelled by feedback? How does the gas's angular momentum affect what structures form? How do black holes at galaxy centers affect their hosts' growth? Each of these questions involves physics we understand imperfectly, with observational constraints that are often indirect and model-dependent. We're uncertain about how to interpret some of Webb's own observations. When we measure a galaxy's brightness and infer its stellar mass, we're making assumptions about the stellar population, the amount of dust. The star formation history. Different assumptions can change the inferred mass by factors of 2 or 3, sometimes more. When we measure a galaxy's size, what exactly are we measuring? The extent of the starlight, which depends on the brightness threshold used, or something more physical related to the underlying mass distribution? Observational uncertainties compound theoretical ones, making some comparisons between models and observations ambiguous. Perhaps most profoundly, we don't know whether our physical laws, tested and verified in the nearby universe, apply unchanged in the extreme conditions of the early universe. We have good reasons to believe they do, reasons based on the success of cosmological models and the absence of any compelling evidence for variation. But we cannot be absolutely certain. The early universe, with its higher densities, higher temperatures, and different radiation environments, might have hosted processes that don't occur today, governed by physics we haven't yet discovered. These unknowns are not admissions of defeat. They're invitations to exploration, to continued observation and theorizing, to the gradual expansion of knowledge through careful measurement and creative thinking. Science advances by confronting what it doesn't know, by transforming mystery into understanding through patient, systematic inquiry. There's something profoundly beautiful about standing at the edge of knowledge, looking out at questions we cannot yet answer, contemplating mysteries that resist easy resolution. Webb's impossible galaxies have brought us to such an edge, revealing a universe that refuses to conform perfectly to our expectations, and there's a strange comfort in this, a recognition that reality is richer than our theories, that the cosmos retains its power to surprise us. Think about what it means that we can see these galaxies at all. Light that left them 13 billion years ago, when the universe was barely born, has travelled across expanding space all that time, preserving information about those distant epochs, carrying it through cosmic time until it reached Webb's mirror and was collected, focused, analysed. That we can stand here, tiny beings on one small world, and detect photons from the cosmic dawn seems almost miraculous, a testament to both the fundamental consistency of physics across time and space, and to human ingenuity in building instruments capable of such detections. The fact that these observations challenge our theories doesn't diminish their wonder, it amplifies it. A universe that perfectly matched all our predictions would be less interesting, less alive, than one that continues to confound and surprise us. The tension between observation and theory drives scientific progress, forcing us to refine our models, to question assumptions, to dig deeper into the physics we thought we understood. Consider how far we've come. A century ago, we didn't know galaxies existed beyond the Milky Way. The universe's expansion was unknown. The Big Bang was decades from being proposed. Dark matter was unrecognized. The cosmic microwave background had never been detected. We had no telescopes in space, no computers to run simulations, no understanding of stellar nuclear synthesis or black holes or the interstellar medium. In just 100 years, through careful observation and brilliant theorizing, we've constructed a comprehensive cosmological framework that explains the universe's evolution from the first fraction of a second through 13.8 billion years of cosmic history. We've measured the age of the universe to within 1%. We've mapped the distribution of matter across billions of light years. We've detected gravitational waves from merging black holes and observed exoplanets around other stars. The scope of our knowledge is staggering, and yet, as Webb shows us, profound mysteries remain. The impossible galaxies remind us that our knowledge, however impressive, is incomplete. There are processes we don't understand, physics we haven't fully grasped, aspects of cosmic evolution that our current models fail to capture. Far from being discouraging, this should be thrilling. It means there's more to discover, more to understand, more beauty waiting to be revealed. There's also something humbling about confronting the limits of our understanding. We are recent arrivals in cosmic history, beings who've existed for a tiny fraction of the universe's age, who've developed science in the last few centuries, who've had the technology to observe the early universe for mere decades. That we've learned as much as we have is remarkable. That questions remain is inevitable and appropriate. The uncertainty also teaches patience. Science doesn't progress through sudden revelations that answer all questions at once. It advances gradually through the accumulation of observations, the refinement of theories, the resolution of smaller puzzles that collectively illuminate larger ones. The impossible galaxy problem won't be solved by a single observation or a single theoretical insight. It will be resolved through years of careful work by thousands of researchers, each contributing pieces to a complex puzzle. There's beauty in the process itself, in the community of scientists worldwide working together on these questions, sharing data, debating interpretations, building upon each other's insights. Astronomy is a collaborative enterprise, with observations from Webb analysed by researchers across continents, with theoretical models developed through international partnerships, with conferences and papers and informal discussions all contributing to the gradual advancement of understanding. Uncertainty also reminds us of the value of multiple approaches. No single method will solve the impossible galaxy puzzle. We need Webb's observations alongside Hubble's earlier work. We need spectroscopic surveys complementing imaging surveys. We need computer simulations informed by theoretical models which are tested against observations that in turn refine the theories. We need studies of nearby ancient stars connecting to observations of distant young galaxies. Every approach provides different perspectives on the same underlying reality, and truth emerges from the synthesis of these multiple viewpoints. The aesthetic pleasure of the images themselves shouldn't be overlooked. Webb's deep fields are stunning, showing thousands of galaxies scattered across space, each one a different island universe, each with its own history. The images remind us that we're not just solving abstract problems, but exploring a real, physical universe of breathtaking beauty. The galaxies are not merely data points, they are actual collections of billions of stars, regions where planets might exist, where the complex chemistry of life might be unfolding, where cosmic dramas of birth and death and transformation play out across billions of years. And perhaps there's something meaningful in the recognition that we are part of this universe we study, that the atoms in our bodies were forged in stars, that we are literally made of stardust, products of the same cosmic processes we seek to understand. When we study galaxy formation, we're studying our own origins, tracing the chain of events that led from the Big Bang through cosmic inflation, through structure formation, through the birth of our own galaxy and solar system, and eventually to us, conscious beings capable of contemplating these vast scales and deep times. The impossible galaxies are impossible only in the sense that they challenge our current models. They are not impossible in reality. They exist. They are there, shining across the cosmos. What needs to change is not the universe, but our understanding of it. And that change, that growth of knowledge, is one of humanity's most beautiful collective achievements. Behind every observation, every theory, every simulation, there are human beings, scientists who've dedicated their lives to understanding the cosmos, who experience the same excitement and frustration and wonder that anyone might feel when confronting profound mysteries. The story of the impossible galaxies is also a story about people, and it's worth taking time to appreciate the human dimensions of this scientific endeavour. The astronomers who first saw Webb's early deep field images experienced genuine shock. Imagine spending years or decades building theoretical models, running simulations, making predictions about what the early universe should look like. Then Webb turns on, the data comes in, and suddenly there are galaxies everywhere, massive and bright, where your model said they should be rare and faint. That moment of realization, that feeling of surprise and excitement mixed with the dawning recognition that years of work might need revision, must have been intense. Some researchers have described it as exhilarating, others as disconcerting, many as both simultaneously. There's excitement in seeing something genuinely new and unexpected. There's also discomfort in having your theoretical framework challenged, in recognizing that assumptions you relied on might be wrong. Scientists are human. They form attachments to ideas they've worked on, take pride in theories they've developed, and can feel defensive when observations question those theories. What's remarkable is watching the community collectively work through these responses, moving from initial surprise toward productive engagement with the new observations. Within months of Webb's first data release, Papers were appearing exploring possible explanations, revising models, proposing new observations to test different hypotheses. The scientific process, at its best, channels the initial emotional responses into constructive investigation, transforming surprise and discomfort into motivation for deeper understanding. The observers and instrument scientists who built Webb and who operate it daily have their own perspective on the impossible galaxies. These are people who spent decades designing, building, testing and calibrating the telescope and its instruments, overcoming countless technical challenges, dealing with budget pressures and schedule delays. Persevering through setbacks. When Webb finally launched and deployed successfully, and when the first images revealed these unexpected galaxies, they must have felt vindication mixed with awe, pride that the instrument they'd created was powerful enough to reveal genuinely new cosmic phenomena. There are also the graduate students and postdocs, early career researchers for whom Webb's discoveries define their scientific coming of age. For a graduate student starting their PhD around the time Webb launched, the impossible galaxies might be the central mystery they work on for years, the problem that shapes their entire early career. Some will make crucial contributions to solving the puzzle, others will work on aspects that turn out to be less central. All will be shaped by the experience of grappling with this profound observational challenge. The collaboration required for modern astronomy is itself noteworthy. Observing programs with Webb involve teams of researchers, often dozens of people spread across many institutions and countries. Data gets distributed to archives where anyone can access it. Theoretical work builds on simulations run by other groups. Incorporating physics modules developed by different teams. No single person understands every aspect of the problem. Progress requires collective intelligence, pooling expertise across many subfields. This collaboration extends across generations. Senior researchers who've studied galaxy formation for decades work alongside early career scientists, bringing fresh perspectives and new technical skills. Students learn from established experts while sometimes questioning assumptions those experts take for granted. The dialogue between experience and innovation drives the field forward. There are disagreements, of course, sometimes vigorous ones. Scientists debate whether specific galaxies are really at the high redshifts claimed, whether stellar mass estimates are reliable, whether simulation results are robust or artifacts of numerical choices. These debates happen in papers, at conferences, in informal discussions, and they're essential to the scientific process. Ideas get sharpened through criticism, weak arguments get discarded, strong ones survive and strengthen. The contentious exchanges might seem aggressive to outsiders, but they reflect deep engagement with the questions, a collective commitment to getting the answers right. There's also the human experience of working with the data itself. Astronomers spend hours, days, weeks analysing spectroscopic observations, fitting models to noisy data, extracting physical parameters from complex multi-wavelength measurements. This work is often tedious, requiring painstaking attention to detail, careful checking for errors, systematic exploration of parameter spaces. It's easy to romanticize scientific discovery as a series of brilliant insights, but much of it is patient, methodical work, the slow accumulation of evidence through careful analysis. And there are moments of genuine joy and satisfaction, when a new observation confirms a predicted pattern, when a simulation finally reproduces an observed relationship after months of debugging and refinement, when a theoretical insight suddenly makes multiple puzzling observations make sense. These moments, though they may seem small compared to the grand cosmic scales being studied, are deeply meaningful to the researchers experiencing them. The impossible galaxies have created opportunities for researchers across many career stages and specializations. Observers design surveys to find and characterize more early galaxies. Spectroscopists develop techniques for measuring precise redshifts and chemical abundances. Theorists explore new physical mechanisms. Simulation experts push computational models to higher resolution and better physics. Statisticians develop methods for inferring population properties from incomplete samples. Each contribution matters, each person's work adding to the collective understanding. There's also something beautiful about how this research connects to deeper human concerns. Why do we study galaxies billions of light years away? Not for practical applications, there are none. Not for economic benefit, there is little. We study the early universe because we are curious, because we want to understand the cosmos we inhabit, because knowing how galaxies form and evolve connects to the deepest questions about existence, origins, and our place in the vast cosmic arena. This curiosity, this desire to understand, is fundamentally human, one of our most distinctive and admirable characteristics. The researchers working on the impossible galaxy problem are, in a sense, asking on behalf of all humanity. Most people will never analyse spectroscopic data or run cosmological simulations, but nearly everyone has looked up at the night sky and wondered about what lies beyond, how it all began. What it all means. The scientists doing this work are, in their way, answering those universal questions, extending human knowledge on behalf of the species, satisfying collective curiosity about our cosmic context. And they do this knowing that final answers may remain elusive during their careers, that the problems they work on might not be fully solved for decades, that their individual contributions are small pieces of a vast collaborative enterprise that extends across generations. There's something noble in that commitment, in dedicating one's working life to questions larger than oneself, questions that humanity will continue exploring long after any individual researcher's career has ended. As we near the end of our journey through the impossible galaxies, it's worth contemplating what comes next, what future observations might reveal, and how the story we've been following will continue to unfold in the years ahead. Webb is not finished. The telescope is operating beautifully, exceeding performance expectations, and it's expected to continue observing for many years, perhaps decades if fuel supplies last and no critical failures occur. Future observing cycles will dedicate thousands of hours to studying the early universe, building on the initial discoveries with deeper, more comprehensive surveys. Several large survey programs are planned or underway, designed to systematically map the high redshift universe. These surveys will observe multiple fields scattered across the sky, going extremely deep to detect fainter, less massive galaxies than the first images revealed. By observing larger areas and reaching fainter limits, these surveys will define the full population of early galaxies, not just the brightest. Most massive examples that dominate current samples. Spectroscopic surveys will measure precise redshifts and detailed spectra for thousands of high redshift galaxies, providing the chemical abundance measurements, kinematic information, and stellar population constraints needed to test theoretical models. These spectroscopic observations are time-consuming, often requiring hours of integration per galaxy, but they provide richness of information that imaging alone cannot match. Webb will also make repeated observations of some regions, monitoring how early galaxies change over timescales of months to years, while cosmic evolution occurs over millions to billions of years, and thus can't be observed directly. Even with decades of monitoring, repeat observations can detect variability from active galactic nuclei, identify supernovae in distant galaxies, and improve photometric calibration through multiple independent measurements. Gravitational lensing surveys are being expanded, exploiting the magnification from foreground galaxy clusters to observe exceptionally faint high redshift galaxies that would otherwise be undetectable. These lensed observations can reveal galaxies with stellar masses below 10 million solar masses, the dwarf galaxies that hierarchical models predict should be the dominant population in the early universe. Understanding the abundance and properties of these low-mass early galaxies is crucial for testing formation models. Complementary observations from other telescopes will provide crucial context. The Atacama Large Millimeter Array, ALMA, observes at millimeter wavelengths and can detect cold gas and dust in distant galaxies, measuring the fuel available for star formation and the obscured star formation that optical and infrared observations might miss. ALMA observations of several early massive galaxies have already revealed substantial gas reservoirs and ongoing vigorous star formation, confirming that these galaxies possess the raw materials needed for their rapid growth. Ground-based extremely large telescopes currently under construction, with mirrors 30 to 40 meters in diameter, will provide complementary capabilities. The Extremely Large Telescope, the Giant Magellan Telescope, and the 30-meter telescope will have collecting areas vastly larger than Webb's, enabling spectroscopic observations of faint high redshift galaxies with detail and precision impossible for space telescopes of Webb's size. These ground-based facilities will be particularly valuable for studying the faint end of the early galaxy population and for making detailed abundance measurements of rare elements that require high signal-to-noise spectroscopy. Future space missions are also being planned. NASA's Nancy Grace Roman Space Telescope, expected to launch in the latter half of the 2020s, will have a field of view 200 times larger than Webb's, enabling wide-area surveys that can find rare objects and map large-scale structure at high redshift. Roman's imaging surveys will identify early galaxy candidates by the thousands, providing targets for detailed Webb spectroscopy and defining the statistical properties of early galaxy populations. Theoretical and computational work will advance in parallel with observations. Simulations are being run at ever higher resolution with ever more sophisticated physics, trying to reproduce Webb's observations while making predictions for future observations that will test the models. Machine learning techniques are being applied to analyze simulation results and to find patterns in observational data that human analysis might miss. One particularly exciting prospect involves detecting the actual moment of reionization as a function of position on the sky. As Webb observes more and more high redshift galaxies, mapping their positions in three-dimensional space, researchers will be able to identify regions that reionized early versus late, seeing the patchy structure of reionization directly. This would provide powerful constraints on what sources drove reionization and how energetic radiation from early galaxies and quasars propagated through the intergalactic medium. Another frontier involves detecting the epoch of the very first stars, population 3 stars, which should have existed before the galaxies Webb currently observes. These first stars might be detectable individually through extreme gravitational lensing that magnifies their light, or their collective effects might be visible as a specific infrared background signal or in subtle chemical signatures in slightly later galaxies. Confirming the properties of population 3 stars through observation rather than just theoretical prediction would be a major achievement. There's also potential for completely unexpected discoveries. Every time a fundamentally new observational capability comes online, from the first large optical telescopes to radio astronomy to X-ray astronomy to gravitational waves, it reveals phenomena that weren't predicted. Webb's unprecedented infrared sensitivity and resolution might detect unexpected classes of objects or phenomena in the early universe, things we haven't imagined because we had no evidence they existed. Some of the most important discoveries in astronomy have been serendipitous, found while looking for something else, or found in data without knowing what to expect. The timeline for understanding the impossible galaxies stretches years into the future. This isn't a puzzle that will be solved in a single breakthrough moment, but rather through the gradual accumulation of better observations, more detailed models, and deeper physical understanding. 5 years from now, we'll have much larger samples of well-characterized high redshift galaxies, improved simulations that better reproduce observations, and refined theoretical understanding of the relevant physics. 10 years from now, the picture will be clearer still, though likely with new mysteries emerging from the ever-deeper observations. What's certain is that the early universe will continue to surprise us, that Webb and future instruments will reveal details and phenomena we haven't anticipated, and that the story of cosmic dawn and the formation of the first galaxies will continue to be written through the interplay of observation, theory, and human curiosity. A story without a final ending, an exploration that will continue as long as we look up at the sky and wonder about what lies beyond. As our journey through the impossible galaxies approaches its end, let's contemplate what we mean when we call them impossible, what that word really signifies, and what these galaxies are teaching us about the nature of scientific understanding itself. They are not, of course, actually impossible. They exist. They shine across billions of light-years of space. Their light reaches our telescopes. We detect them, measure them, study them. In the most fundamental sense, they are utterly, undeniably real. The impossibility lies not in the galaxies themselves, but in the gap between what they are and what we expected them to be, between cosmic reality and human theory. This gap is instructive. It reminds us that our theories are models, simplified representations of reality designed to capture essential features while ignoring details. All models involve assumptions, idealizations, approximations. we assume star formation efficiency takes certain values, that dark matter behaves in specific ways, that feedback processes regulate themselves according to certain prescriptions. These assumptions are educated guesses based on observations and physical understanding, but they are still guesses, subject to revision when new evidence demands it. The impossible galaxies are teaching us where our assumptions broke down, which simplifications went too far. What complexity we failed to capture. This is valuable knowledge. Every failure of a model to match observation is an opportunity to improve the model, to incorporate overlooked physics, to refine our understanding. The history of science is filled with such moments where observations contradicted prevailing theories and forced theoretical revision. Think about what happened when astronomers first measured galaxy rotation curves and found that stars far from galactic centres were moving too fast to be held by the gravity of visible matter. The observation seemed impossible given the known matter content of galaxies. But rather than dismissing the observations, astronomers took them seriously and proposed dark matter, revising their understanding of cosmic mass content. Now, dark matter is a cornerstone of cosmology, crucial to explaining structure formation, gravitational lensing, the cosmic microwave background, and much more. The impossible rotation curves led to a fundamental advance in our understanding of the universe, or consider the accelerating expansion of the universe. Discovered in the late 1990s through observations of distant supernovae, the expansion was supposed to be slowing down due to gravity. Acceleration seemed impossible, but the observations were solid, confirmed by multiple independent teams, and they led to the introduction of dark energy, another fundamental component of our cosmological model. Again, the impossible became the pathway to deeper understanding. The impossible galaxies may be leading us towards similar advances. Perhaps we'll discover that dark matter has properties we didn't know about. Perhaps we'll find that star formation in the early universe operated according to different rules than it does today. Perhaps we'll identify new feedback processes or new modes of gas accretion. Perhaps we'll refine our understanding of cosmic inflation or reionization or black hole formation. Whatever specific revisions emerge, they will represent progress, growth of knowledge, a more accurate and complete understanding of how the universe works. There's also a deeper lesson about the relationship between theory and observation. Theory without observation becomes untethered from reality, potentially elaborating elegant mathematical structures that have no connection to the actual universe. But observation without theory becomes a disconnected collection of facts with no organising framework to make sense of them. Science advances through the interplay between the two, with observations testing and constraining theories, and theories guiding what observations to make and how to interpret them. The impossible galaxies represent a moment where this interplay is particularly dynamic. Observations have outpaced theory, revealing phenomena that current models struggle to explain. This forces theorists to work harder, to explore new ideas, to question assumptions they previously took for granted. Eventually, through the iterative process of proposing modifications, testing them against observations, refining them, and testing again, a new theoretical consensus will emerge, one that accommodates both the new observations and the previous successes of earlier models. This process is not instantaneous. It requires patience, careful work, and intellectual humility from all involved. Observers must ensure their measurements are reliable, that claim detections are real, that error bars are honest. Theorists must be willing to revise cherished ideas when evidence demands it, while also maintaining appropriate skepticism about new observations that might contain errors or be misinterpreted. The community must remain open to different approaches and ideas, while also maintaining standards for what constitutes compelling evidence. What the impossible galaxies ultimately teach us is that the universe is more complex, more varied, more interesting than any human theory can fully capture. Our models are approximations, useful and often remarkably accurate but always incomplete. Reality always retains the capacity to surprise us, to reveal aspects we hadn't anticipated, to challenge our assumptions. And this is as it should be. A universe completely explained with no remaining mysteries would be a poorer place. The fact that profound questions remain, that new observations continue to puzzle us, that our theories require ongoing refinement, keeps science vital and alive. It means there's always more to discover, more to understand, more wonder to encounter. The galaxies are impossible only until we understand them. Then they become possible, incorporated into an expanded framework of knowledge, no longer mysterious but explained. And yet in becoming explained, they'll inevitably reveal new mysteries, new puzzles, new impossible things that we'll work to understand in turn. This is the endless cycle of scientific exploration. The perpetual pushing back of the boundaries of knowledge, the transformation of the impossible into the understood, again and again without final conclusion. We are privileged to live in a time when instruments like Webb can show us the early universe with unprecedented clarity. When we can observe the cosmic dawn and test our theories of galaxy formation against actual data from that distant epoch. Our ancestors could only speculate about such things. Future generations will have even better observations and more refined understanding. But we are here now at this particular moment in humanity's exploration of the cosmos, witnessing the impossible galaxies and participating, through our attention and wonder, in the collective human endeavour to understand the universe that gave us birth. We've travelled together through a remarkable story, haven't we? For 2.5 hours we've explored one of the most profound discoveries in modern astronomy. 300 galaxies that challenge our understanding of how the universe evolved from simplicity to complexity. We've journeyed from the cosmic dark ages through the first stars and galaxies, examined the evidence that makes these galaxies so puzzling, explored the theoretical framework struggling to explain them, and contemplated what they teach us about the nature of scientific knowledge itself. From the initial shock of Webb's first images showing massive galaxies where models predicted they should be rare, through the detailed spectroscopic confirmations and the recognition that these weren't measurement errors but genuine cosmic phenomena, to the ongoing theoretical work trying to refine our understanding, we've followed the arc of scientific discovery in real time. We've seen how observations can upend carefully constructed theories, how the universe refuses to conform perfectly to human expectations, and how this resistance to explanation drives scientific progress. The answer, as honestly as I can give it, to the question of why these galaxies exist is that we don't fully know yet. We have clues, certainly. Star formation was probably more efficient in the early universe, gas accretion rates were likely higher, feedback processes might have operated differently, dark matter might have properties we haven't fully accounted for. Initial conditions from cosmic inflation might have been slightly different than standard models assume. Black holes might have formed through pathways we haven't recognised. The truth likely involves some combination of all these factors, a complex interplay of physics that we're still working to disentangle. But perhaps what matters most is not having a final answer, but appreciating the journey toward understanding. The impossible galaxies have revealed how much remains to be discovered about the universe, how our knowledge, however impressive, is still incomplete. They've shown us that the cosmos is more complex and more interesting than we imagined, and they've provided direction for future research, questions to answer, observations to make, theories to refine. If you found these slow explorations of cosmic mysteries meaningful, a like and subscribe helps others discover these peaceful journeys through deep space and deep time. I make these videos because I believe there's value in approaching profound questions with patience and contemplation, rather than sensationalism, in acknowledging uncertainty rather than pretending to false certainty, in finding wonder not despite the limits of our knowledge but within those very limits. And to those of you who've been here before, who return to these quiet examinations of the universe, thank you. Your presence, your attention, your shared curiosity mean more than I can adequately express. Wherever you are in the world right now, whatever your circumstances, I hope you found some measure of peace in this contemplation of distant galaxies and deep cosmic time. I hope your breathing has slowed, that your thoughts have quieted, that the concerns of the day have receded, at least for these hours we've spent together. I hope your body feels heavy and warm, ready for rest. Look up at the night sky, if you can, or imagine it if you cannot. All those stars, all those distant galaxies, each one a universe unto itself. And somewhere among them, 13 billion light-years away, the impossible galaxies shine. Those ancient assemblies of stars that formed when the cosmos was young, that challenge our understanding and invite our wonder. They existed for billions of years before humans evolved, before Earth formed, before our sun ignited. They will exist for billions of years after we're gone. Unless they merge with other galaxies or are torn apart by gravitational forces, their stars continuing to burn long after our civilization has vanished into cosmic history. And yet, through the light that's travelled all that distance, across all that time, we can see them, study them, learn from them. We can connect across billions of years and billions of light years through the patient journey of photons and the ingenuity of telescopes and the curiosity of minds that wonder about cosmic origins. This connection, this ability to observe and understand, is one of the universe's most remarkable features, matter becoming aware of itself. The cosmos studying its own history through conscious beings that emerge from stellar forges. The impossible galaxies are teaching us that the universe is deeper, stranger, more beautiful than any theory fully captures, and that our exploration of it, our attempt to understand how we came to be here in this vast cosmic arena, is one of humanity's most meaningful endeavours. It's a journey without final destination, an exploration that will continue as long as there are eyes to look upward and minds to wonder at what they see. So let that thought settle gently as you drift towards sleep. You're made of stardust, atoms forged in stellar cores, scattered by supernovae, gathered into planets, assembled into complex molecules and eventually into you, a conscious being capable of contemplating your own cosmic origins. The universe made you, and now you're aware of the universe, thinking about how it all began, how galaxies formed, how stars ignited, how everything you see came to be. It's a remarkable loop of existence and awareness, matter and meaning, cosmos and consciousness. Sleep well. Dream of ancient light from impossible galaxies, of stars forming in the cosmic dawn, of the endless churning evolution of the universe from simplicity to complexity, from uniformity to structure, from darkness to light. Dream of the patient work of gravity assembling matter into galaxies and stars and planets and life. Dream of the long history that connects you to the Big Bang through chains of cause and effect stretching across billions of years. You're part of this story, a brief but genuine participant in cosmic history, your awareness a fleeting gift of atoms assembled just so, conscious for a moment before returning to the universal flow. Good night.